Okay, so we're trying to address this question here about why Venus is so hot. So here's sort of the scenario on Venus. Here, of course, is the surface of Venus right here. I label it with a V, and there's all this nice sunlight coming down. Now what happens, of course, is the sunlight, as we saw, will more or less pass through the thick carbon dioxide of Venus down to the surface. And we mentioned that the infrared will scatter off of the carbon dioxide molecules, as we saw when the molecules got all jumpy when hit with infrared photons. But let's just hold off on that just for a moment. Let's instead examine what happens right here at this level when the visible light right here, this is all visible right here, sort of runs into and interacts with rocks. Okay, so what happens, of course, right here at this interaction point is the visible light comes down, and you know what rocks look like when they're hit with light. You can sort of see them. Maybe they shine or you see colors or whatever. That's certainly part of the process of reflection. But what rocks tend to do, just sort of what they do then, is they take the visible light here, the visible light, and they absorb a lot of it. And what they do is reflect then, let me draw this maybe in this orangish color here. What they reflect back out, and the reason why I'm not drawing this in yellow is because I'm going to label it IR. So the IR light that hits rocks gets reflected. It's almost like rocks don't like IR light, so they absorb much of the visible and so on and send the IR back up. That sort of creates an interesting prospect here now, because what you have here on all planets, not just Venus, but certainly Venus is the case of this here, is you have these rocks here that are sending this infrared light, so the IR, as you can tell, goes back up. Okay, that's sort of an important step here. Here's the visible light coming down, or just light from the sun, whatever you want to call it, comes down like this. And the IR component of the light gets reflected back up by rocks. Okay, so that's kind of interesting. And so what of that? Well, what happens now is the infrared light that comes back up, let's just take maybe this little branch of infrared light right here, maybe take this little part right here, as it travels up and travels up and travels up, it might encounter some of that CO2 that's in Venus's atmosphere. Like this is a CO2 molecule right here. So as we saw then, we have sort of the perfect example here. Here comes some IR light hitting a CO2 molecule. And we saw in that animation what happens when IR light hits a CO2 molecule. Well, the CO2 molecules tends to send the infrared light in all directions. Sort of it scatters it. Some will go here, some will go here, some will go here, some will go here. And most importantly for our argument here, some of it will go back down. Let's just label that special one in blue here. This part of the IR light here that hit the CO2 molecule went back down. So that means this IR light here is going back down, might hit the rock again, and get sent back up. And so you can already sort of tell what's happening here just in this little diagram that I drew here, indicating what happens around this single CO2 molecule. If you look very carefully just inside this pink circle here, you can see that the IR light is sort of starting to become a bit concentrated. And IR light is normally associated with heat. So if you have IR light becoming concentrated in some region, say near the surface of a planet, and IR light is associated with heat, well, there's going to be a concentration of heat. And so I will show you how that works now. I guess this video is getting long enough. In the very next video, I'll show you an animation about how this works.